Thank you for joining us today. Thank you for investing your time in this demo. What you're going to see today is an application of TCG technology to enhancing the security and trustworthiness of a converged network of IoT devices and cloud management applications. This demo is done as a joint effort by Cisco, Infineon, and Intel with the assistance and support of HSR University of Applied Sciences in Switzerland. The demo is shown live, will be shown live on April 20th at the RSA conference in San Francisco. TCG hosts a free half-day seminar. We have room for about 1,000 people there, and we hope to fill the house. This is one of 20 demos that will be shown along with panel discussions and other seminars that will be part of that activity. A number of those demos will be focused on this topic of securing IoT with trusted computing. My name is Stacy Kennedy. I work for Cisco, and I am Cisco's representative on the board of directors for Trusted Computing. We'll begin by a discussion of the agenda that we've got for this time. It's pretty straightforward. We're going to have an introduction, a brief discussion of the problem that we're trying to solve here, followed by 7 or 8 slides that describe the demo, describe what you're going to see, and then finally we'll go to the demo itself. So this is a proof of concept done by these 3 companies in association with HSR. The nature of this is that we want to prove what's possible in terms of live application of TCG standards in products that are in the market today to solve a specific kind of problem in this particular case and solicit customer feedback. So what we're interested in from you as a viewer is your opinion of what you saw. We're not selling anything because this is just a proof of concept. We might someday sell something based on what we hear from you as customers. So please don't hesitate to leave us feedback on this demo. The nature of the problem that we're addressing has to do with a strong current of convergence that we see in the IoT space and the cloud space. We're seeing a large number of companies that have this convergence occurring. So for example, smart buildings in Manhattan, they may contain tens of thousands of sensors and actuators that control heat, light, elevator, cameras. These smart buildings and their collections of sensors are not necessarily managed by an application that's found in the building. They could be managed across the internet, maybe by a management company that is based in Dallas. So we see a convergence of sensors and actuators deployed by a company remote from the management and analysis facility, wherever that may be across the cloud. It's not just smart buildings. This could be oil pipeline management. You might have the oil pipeline from New Orleans that carries refined product to Raleigh for distribution in the southeast region of the United States, and that is managed out of, I don't know, Houston probably. So there's also examples of fleet management of vehicles, airplanes, trains, vehicles of any sort, and there are many other use cases in which we find this remote deployment of sensors and actuators feeding their data back to a management facility which directs their behavior from there. In some cases, these converged activities represent safety and security concerns. The oil pipeline, for example, we certainly don't want that to be tampered with, and that means that the owner of that pipeline may find it of use to have some evidence that the devices that are reporting back to his data center are the devices that he owns, not a foreign device that's been inserted into the network. And even if he owns it, he might further want evidence that the devices that he's dealing with are configured and have the software inventory that he expects them to have. In other words, they do what he expects them to do. They haven't been modified by some unknown party to do something else. And finally, we've got this notion here, it would be nice if these devices were actually authenticating to the network in an autonomous fashion. And for those of us on the call who are aware of basic principles of data security and authentication, you know that there are three basic ways to authenticate. One is what you know, one is what you are, and one is what you have. Any one of those used in authentication is by definition weak. Any two or more is by definition strong. And what you're going to see here is strong authentication in a machine-to-machine environment. So as I mentioned before, this is going to be a demonstration of a deployment of IoT devices. The central management for that deployment of devices is remote, located across the internet. And we are going to use strong authentication as a way of demonstrating that the devices that are connected to the network are known to us, in other words, they belong to us, and that the software and configuration of those devices is also known to us. In other words, they have integrity. And as I mentioned, this is the specific example for this is smart buildings. There are many other examples. This is just one of them. And here's a layout of our demonstration network. In the top left, you see that our IoT deployment is represented by Raspberry Pi devices. If you look closely in that photograph of the Raspberry Pi, you'll see that the card that is inserted vertically into the Pi motherboard is supplied by Infineon, and there is a TPM, a Trusted Platform Module, on it. This Trusted Platform Module is a hardware security module that provides services essential to the demo. For example, it protects the digital certificate that is used by the Pi and all of the devices in the demo to prove who they are. It also protects integrity information, which is the second form of authentication. This integrity information is stored in a set of registers inside the TPM. These registers can be written to only during boot of the device, only by firmware in the device, and they can be read subsequent to boot by any application that's interested. We also, the Raspberry Pi, the deployment of IoT devices, is talking to a Cisco CGR 1120 router. This is an industrial-grade router used in deployments like this to talk directly to IoT devices. The router, in turn, talks to a server. In a deployed situation, this server would be located across the net, and when you are present at the demo in RSA, that will be the case. But it doesn't have to be that way, of course. We could have a manufacturing facility, in which case the IoT deployment is a set of industrial control systems on the factory shop floor. The CGR is bridging the telemetry and management information out of that manufacturing floor deployment into a set of servers where the telemetry is processed and new instructions are directed out. And this is very common in large manufacturers, for example, Boeing. So that's the equipment layout and the equipment that we will be using for this demo. This is the authentication flow between the Raspberry Pi and the CGR. It is different between the CGR and the server, as you'll see in a moment. The authentication flow here is the Raspberry Pi is going to prove its identity and integrity to the CGR. The Raspberry Pi, the IoT deployment, implicitly trusts the CGR in this flow. We're not saying that this is the way it has to be, and in fact, in this model, the CGR represents a single point of failure because everybody is forced to implicitly trust it. You'll see in the flow between the CGR and the server that we solve that problem by mutual verification of identity and integrity. But we wanted to make sure that we showed all the options that are possible here. The software that's involved in performing these validations is TLS, and an open source set of implementations of the Trusted Network Connect protocols specified by TCG. That open source set of implementations, it goes up by the name StrongSwan, one string, StrongSwan, and can be found at strongswan.org. Let's continue now with a discussion of the authentication flow between the Raspberry Pi and the CGR. It starts with the Raspberry Pi requesting access, requesting a session with the CGR. The CGR responds with, please give me your certificate and your integrity report. The Raspberry Pi does so by signing the information that it provides using an asymmetric private key that is stored within the TPM on the Raspberry Pi. That private key never leaves the TPM. So the signature here becomes evidence that it is in fact this Raspberry Pi, not any other device that is providing the information. The CGR does a standard TLS certificate validation for the certificate that is provided. For the integrity report that is provided, it does a local validation using a TNC attestation server that is running on the CGR. If the validation comes out clean, the session is authorized, and we will see that the Raspberry Pi now has the ability to open a session through the CGR to the server. As I mentioned on the previous slide, the authentication flow between the server and the CGR is different. For the RPi and the CGR, we have a single point of failure, the CGR, which is implicitly trusted by all the IoT devices. In the case of the server and the CGR, we have platforms that have a lot of resources, and we want to demonstrate that we do not have to have an implicitly trusted server in the deployment. And this represents new innovation shown by this demo. There's nothing in the specs that precludes this notion of mutual validation of identity and integrity. It's just that no one's done it before. So watching this demo and seeing it at RSA, you're seeing something that hasn't been done in industry before. So how is this different? We've got the server supplicating to the CGR, can I have a session? And this time the CGR responds with, give me your credentials and here are mine. The CGR and the server both have TPMs, and in this regard they are behaving the same as the Raspberry Pi in terms of how they protect the credentials that they are using. The next step is that both of these platforms verify both of these credentials. They both have the capability of doing a standard certificate validation using TLS, and they both have local TNC attestation servers running on them that are validating the integrity reports. If both parties are happy with both credentials, a session is authorized, and now we can have an end-to-end connection between a server and the Raspberry Pi through the CGR. This slide is just a brief notion of what the specifications are that are involved in this authentication. You will see that this architecture is layered, similar to the OSI Network 7-layer model, if you are familiar with that. If we read it from the bottom to the top, we see that at the bottom we have a packet flow layer similar to layer 2. Above that, we have a message flow layer, and then finally we have an application layer in which we see that on one side we have an integrity measurement collector, and on the other an integrity measurement verifier. This slide is a brief discussion of the network topology, taking into account the presence or absence of TPMs, where clients and where validation servers are located, and a little bit of a notion of how this network defends itself from outside devices. So if we read across the top here, we have a demonstration of a Raspberry Pi, and it's being used as a sensor in this case. That's what that little camera icon means. The red line shows that we've got a flow of video telemetry through RASP 1 to UCS 7. In this flow, the flow doesn't actually start until TNC has had its chance to validate all the devices in the path. So on the Raspberry Pi, we have a TNC client, we have a hardware TPM, and we have Linux Integrity Measurement Architecture used as the method for measuring the integrity of the operating system components. You may be aware of TPMs and how they are used in PCs. The way they are used in PCs is to measure the integrity of BIOS and the OS loader only. If you have a Windows 8, it'll go a little bit further and measure some of the early launch components of the Windows operating system. This is another unique feature of this demo. We're showing that you can use a TPM to conserve the integrity measurements of anything you want in the operating system. That can be operating system executable files that are part of the standard operating system. It can be application executable files, and it can be configuration files that are present for whatever purpose. So it's possible for the customer to make decisions about what they want to do in terms of attesting the integrity of the Linux operating system and applications that are in it. So IMA measures components of the operating system and stores those measurements in the TPM. The firmware on the Raspberry Pi can also measure firmware, the firmware inventory of the Raspberry Pi, and store those measurements in the TPM. The TNC client communicates all of those measurements on demand to the Cisco CGR, where the TNC server on the CGR will validate the integrity data reported by the Raspberry against its expectations, golden measurements that the TNC server has and are protected in the policy database. If the validation occurs successfully, the Raspberry Pi will have a session now, a TLS session, with the CGR. And notice that we are using PTTLS for this connection. It's also possible under the specs to use EAP. In this case, we chose not to do so. The mutual authentication is shown between UCS7 and the CGR. In this case, both sides are providing information to each other for validation, and so we see that the UCS7 has a policy database that it can access. And notice that we have a software TPM on the UCS and that we are using tboot on the UCS. Tboot is a mechanism for reporting using the TPM to record integrity information and then reporting that information. In this particular case, we chose to implement the UCS server-based code in a virtual machine. Because of that, we do not have direct access to the hardware TPM, and we are using a software TPM emulation in the UCS. The same is true on the CGR. You'll notice at the bottom of the CGR box, we're using tboot. We have a software TPM and the TNC client on top of that. Within the TCG TPM specification, it is legal to use a software implementation of a TPM if the software implementation is operating is executed in a secure operational context. For the purpose of this proof of concept, that's not really true on the Cisco CGR or in the UCS. Work continues to make that possible, but for the purpose of a POC and for the purpose of eliciting customer interest in this, we believe that as long as we've got full disclosure, we're okay taking this approach. Now, one last thing here on this slide, notice Raspberry 6. Raspberry 6 doesn't have a TPM. Raspberry 6 is actually a lying endpoint. It doesn't belong in this network. It was placed there by a foreign individual, someone not part of the company. In this particular case, the Raspberry 6 can perform IMA, and there might be some sort of integrity information available, but what Raspberry 6 does not have, does not have two things. One, it doesn't have a TPM-protected private key that is known to the network. In other words, the network cannot validate a certificate that might be provided by Raspberry 6. So this network can't recognize Raspberry 6. That alone would preclude Raspberry 6 from being included in the network. But problems don't stop there for the attacker. In addition to not having a certificate, he also doesn't have an integrity measurement that is recognized by the policy engine. So he's got both of these problems to overcome if he's going to successfully insert Raspberry 6 as a fake endpoint in this network. We're now going to move to the demonstration part of this. We're going to discuss a few snippets from syslog showing pertinent information when these devices start. First of all, remember I told you that elements of the operating system are measured, and those measurements are stored in the TPM. And this slide goes to how that's done. If you're familiar with TCG protocols, you know that measuring means taking a cryptographic hash of the file in question or of the files in question. You may also be aware that typically when measuring BIOS, a block of BIOS code is measured consisting of perhaps many BIOS programs, and that consolidated measurement is extended or written to the PCR. In this particular case, when we're measuring the operating system, what we are doing is iteratively measuring specific files in the operating system. And if you look down in the lower right-hand corner where it says number 1, hashed file, you can see the list of files rolling by in syslog that we are iteratively hashing. After a hash measurement is made of each file, you can see that hash measurement listed in 2, hash of file. That hash is then extended into a PCR, that's shown in 3. And then finally, the PCR that we are extending into is PCR 10. So you can look at syslog for the definitive list of everything that we are measuring and extending into PCR 10. When IMA completes during Linux boot, PCR 10 has the consolidated hash of all of the files that IMA measured. Now, in terms of a problem, let's say that this PCR value is validated in the CGR and found to be incorrect. It doesn't match the golden value. We don't know why. We don't know which file didn't match correctly. What we know is that something is wrong. And this particular device, this RPi in this case, is excluded from the network. We have captured the information, so if you want to go back as the administrator or the forensic investigator, if you want to go back and find out what file was corrupted, we have that information for you. And in this particular demo, what you'll see is we've got 2 options actually for interrogating the integrity reports. One is to look at all of these hashes and one is to look at PCR 10. And we'll see what the difference is shortly. This is just a syslog snippet of typical TLS certificate validation. We haven't done anything to modify that process other than add hardware-based protection for the certificate on the device where the certificate is stored. This particular part of authentication is what's new. Here we have a syslog snippet of the processing that occurs when an integrity report is being validated. We see some TNC messages, and if you follow the red arrow that's present in the black field, you'll see here that TNC access recommendation is access allowed. That means that the TNC validation server has received an integrity report, compared the content of that integrity report to the expected values that it protects within its own database, found a match, and said, hey, this guy's okay. We'll talk to him. All right, so now we're going to move to what information is stored on these machines and how is that information being used. We're using the StrongSwan site. For this portion of the demo, we've used port forwarding to make sure that the information from the CGR and from the server are forwarded to StrongSwan so that we can take a look at it. You don't have to do it this way. You can either run a web server on the CGR on the server so you can go directly to those, or you can forward the information from those devices to some management server of your own design. So in this case, we're looking at the CGR, and we are going to consider the golden measurements that it has. So we're going to start by looking at the directories. Remember, I told you that IMA is being used to measure the content of directories on the Raspberry Pi. This is going to be the golden set of measurements used to validate what the Raspberry Pi reports. So here's all of the directories that IMA is measuring on the Pi. And we're going to click on /bin, the /bin directory. Here are all the files in /bin that are being measured by IMA on the Raspberry Pi in this case. We're going to pick bash, a popular executable. Here we see the specific information related to the /bin/bash file on the Raspberry Pi as recorded in the golden measurement database on the CGR. We see that in this particular case we've got both SHA-1 and SHA-256 measurements Keep in mind, this is a proof of concept. We're showing as much as we can. So we've got this kind of information stored for all of the files in all of the directories that are on the Raspberry Pi that we have an interest in. Okay, now we're going to move back and take a look at the information that's recorded about the Raspberry Pi device. So we'll click on Devices. We see in this screen that we've got a couple of server images running and we've got one Raspberry Pi. So we're going to click on the Raspberry Pi first. Now, let's take a look at this ID. What is this ID? We're going to use some TCG lingo here. When the Raspberry Pi was provisioned, one of the things that was done was the TPM was directed to create an attestation identity key, an AIK. When the Raspberry Pi reports information, integrity information, to the CGR, it uses the private portion of the attestation identity key to sign the integrity report before it is sent to the CGR. The CGR is going to use the public key in order to validate that it is in fact RASP 2 that has provided that integrity report. The set of numbers here that we see in this ID field is specifically the SHA-1 hash of the public portion of RASP2's AIK. That makes this ID a hardware-protected identity for this device. And we see the human name for the device, and we see a little bit more information about the device here. So that's what we know about this device so far. And next we're going to click this device report to get a little bit more information about RASP 2. All right, on this screen, a little bit more detail about RASP 2. We can see the full ID, which is a SHA-1 hash of the AIK public key for RASP 2. And we see that the most recent session was March 23rd. Let's take a look at that recent session and let's see if we can find out a little bit more detail about what happened when the RASP 2 tried to connect to the CGR. Notice this line here, the TPM IMA measurements. We see first of all that the session was permitted, allow, so the validation occurred successfully. Over here, under the comments, we find out what exactly was being done here. We see that the CGR validated the hashes for 299 files. Of those 299 files, actually 288 were recognized as measurements that were expected and found in the golden measurement database on the CGR. We also find that there were 11 unknown. What's that mean? So this was included because there can be a process in which the customer decides what files are important and what files should be measured. Likely, if this was a product, then the device manufacturer would have made decisions about all of the files on the device that should be measured, and would have provided that as guidance to the customer, possibly as a preset for the customer. The customer might just accept it as it is, or he might say, well, you know, I like that, but I want to add my configuration file to it. So just imagining how this might play out in production at the OEM and then in use at the customer site, we would say that the OEM thinks that there should be 288 files. The customer thinks that there should be 11 additional files, and the customer is currently testing his system. He doesn't want it to be rejected, which might happen if we were validating only against the consolidated set of measurements found in PCR 10. Since the customer is testing, he might want to go through this a few times until he's confident that the golden measurement database has 299 measurements in it, and this is where he finds that out. With that knowledge in place that he is in fact validating everything he thinks he's validating, he could go to the more efficient mechanism of validating just PCR 10, which contains the aggregate of all of the hash measurements. I'd like to point out one other feature of IMA that is relevant here in terms of validating the integrity of these IoT devices. IMA operates in a continuous fashion on the operating system. That means that it records changes to files as the system is in operation. That means that even though the system might have been clean when it was booted, we can continuously monitor the status of this Raspberry 2 device to assure ourselves that it is still clean even though it's been a year since its last boot. So what will happen there is that we've got Raspberry 2, it's a camera. We are sensitive to the continuous feed of data from that camera. We don't want an interruption. And we can accomplish that by simply using a revalidation request from the CGR to Raspberry 2, wanting to know, has your integrity changed? The Raspberry 2 will respond with its current measurements of the files, these 299 files in this case, which can then be revalidated by the CGR. And if all is well, then nothing that we care about has changed on the Raspberry 2, and we can continue operation. If we find that there has been a change in a sensitive file, we can then raise an alert or take other action. We can't trust the Raspberry 2 anymore. So that's something that is not going to be possible when we move on and take a look at what happens with the server. Now we're going to back up and take a look at what happens with information from the UCS server. Here we have the devices menu again. We have a couple of UCSs. Let's take a look at UCS VM image 8A. So we're not actually looking at the server's integrity in this particular proof of concept. We're looking at integrity information stored in a VM called UCS 8A. All right, once again we see an ID, and this is the SHA-1 hash of the AIK public key associated with UCS 8A. If we take a look at the device report for UCS 8A, we see down here that we did a TPM T-boot measurement. And let's talk a little bit about what we've done for this proof of concept and what the proof of concept is emulating here. So we're talking to a virtual machine, and we are using a pre-recorded integrity report that originated from Intel's trusted execution technology, which is used on this UCS server. TXT, Trusted Execution Technology, validates the integrity of the hypervisor on this server at time of boot. This produces an integrity report that can be extracted and then used as an integrity attestation for the status of the server when it came up. Now, on the RPI side, we said we have IMA, and we can do some continuous measurement there over the uptime of that device. Here, we are doing something that is a little bit more static. It's more it's measured at time of boot. And as I said, we are extracting that report and providing it to the VM in a manual way. In order to do this automatically, we would have to place the attestation server in the hypervisor. We thought that might not be a good idea. Or we would have to have a virtual TPM associated with the server, and that can be possible, but we were not able to finish it in that work in time for this proof of concept. Now, with regard to continuous validation of the integrity of a T-boot environment, a trusted execution technology environment, we are aware of a way to do that, but we have not implemented that for this demo. It turns out that trusted execution technology can be directed to do a warm boot. And what happens in that case is all of the pages are paged out, activity on the server halts while Intel's hardware and firmware revalidates the status of the hypervisor against the original information that it had for it. So it's doing a revalidation of the hypervisor at that moment, and at that moment the integrity report is updated so that it can be revalidated. That gives you something along the lines of IMA, and if continuous validation of the server is important, it gives you a way to get at that concept. All right, so that concludes our demo. What you've seen here is mutual authentication from point to point across a network. The authentication is multi-factor. That is based on the identity certificate that is protected by dedicated hardware on each device, and the integrity report that is also protected by that hardware. We've seen that we can interrogate what files go into that integrity report. We can modify them. They may be executable files, they may be configuration files, they may be operating system files or application files. We've also seen that it's possible to continuously validate the integrity of the platforms in this system using either IMA or TXT features. And that as a consequence of this, the platforms that are participating in this network, this converged IoT to cloud application, all know each other and all trust each other. We didn't demonstrate the ability to dynamically reject a platform that was originally trusted and lost integrity during use, but it is technically possible. We hope that you enjoyed this demo, got a lot out of the demo, and we solicit your feedback. Is this relevant in your environment? Remember, proof of concept, we're not going to sell you anything. We just want to know if you found value in this. And we want to know why. We don't care so much whether you found value or not, as long as you include in your comments why you feel the way you do. Thank you for your time. We hope to hear from you.